Hello everyone. I would like to talk through a proof of the theorem for the measure of an inscribed angle. This theorem states that the inscribed angle, which is an angle that has a vertex that is on the circle, the measure of the inscribed angle is 1/2 the measure of its intercepted arc. So the proof to this theorem actually involves 3 different cases because we can have 3 different kinds of inscribed angles. So I drew out 3 circles here just to overview our 3 different cases. So case 1 is when our inscribed angle, one of the sides of it actually goes through the center of the circle. So something like this. So one of the sides goes through the center, and then the other side is just somewhere else. So here's an inscribed angle, the vertex is on the circle, and what the theorem is stating is that this angle is half as big as this arc. So that's one case. Our second case is if the center is in the middle of our angle. So again, maybe we have an inscribed angle, and now the 2 sides of the angle go around the center of the circle, like so. But again, the theorem states that this is half as big as this arc. And then the last case, this one is when the center of the circle is outside of our inscribed angle. So now the 2 sides of the inscribed angle are both kind of on the same side of the center. Okay, so for each of these, what we're looking at is that this angle, maybe this is x, the arc is twice as big, so that would be 2x. If this is x, the arc is 2x all the way through. Okay, and we need to justify it in these 3 cases. So I just want to do kind of not a completely formal proof, but I just want to describe the process you would take. So let's go case by case, and we want to justify this for each of those. All right, so the first case, we're going to take a look at the one where our center, one of the sides of our inscribed angle goes through the center. Okay, so I want to just label a couple things here. So I'm going to label the central angle, let's label this as, we'll say theta. And then our arc, let's label this as alpha. Okay, so we want to show that alpha is equal to 2 times whatever theta is. Okay? Now I'm going to draw in one other segment here, just so we have this to work with. So if I draw in this segment, we know that based on the way that we define the measure of an arc, the arc has the exact same measure as the central angle. So if this arc is alpha, the central angle is also alpha, however big that happens to be. Okay. Now let's take a look at what else we've drawn here. So we actually have 2 radii. So from the center here, and then the center to this point, these are both radii, so that means that these are congruent to each other, which means that this is an isosceles triangle. So if this angle is theta, according to the base angles theorem, this one also has to be theta. Okay? Now the one other piece that we need is right here. this other angle inside the little isosceles triangle that we've drawn, because this is a diameter, the way we set it up for this case, I know it goes through the center, I know that this is a straight angle. So this entire thing is 180, which means that this angle is 180 minus whatever alpha is. Okay? So now, according to the triangle sum theorem, if I add these three angles up inside my triangle, I should get 180. So theta plus the 180 minus alpha, altogether that has to be 180 degrees. And that's the triangle sum theorem. So let's take that equation and we'll do a little bit of simplifying. Theta and theta together is 2 theta. Okay. I can subtract 180 from both sides. So that gives me 2 theta minus alpha is equal to 0. And then let's add alpha to the other side. And what we end up with is 2 theta is equal to alpha, which is what we wanted to show. So that means that this inscribed angle here, theta, is half as big as this angle. So for example, if this was 50 degrees, let me change color. So if this was 50 degrees, what this is saying, 2 times 50, this inscribed intercepted arc, this would have to be twice as big, so that would have to be 100. Okay, so that takes care of the first case. We ended up with what we wanted to show, and we're actually going to use this to help us in our other two cases. So we have already justified this one. So let's move on to case 2, which is where the center of the circle is in the inscribed angle. So again, I'm going to label. So let's say that this is theta, and then our arc, we'll call that alpha. And still, we want to show that alpha is equal to 2 times whatever theta is. Now, we actually have to be a little bit clever in this case. As I said, we want to use case 1 to help us in case 2. In case 1, we needed that diameter. So I'm actually going to split this up here. Actually, so if I were to draw in these segments first, so here to here, and then almost straight, but not quite. So that central angle, this would also be alpha. But what we want to do is I want to draw in this diameter. Okay, going down the middle of our inscribed angle. Okay, and what that's doing is it's actually splitting up our inscribed angle in 2 pieces, and it's splitting up our central angle into 2 pieces as well. So let me label some things to make it easier to work with. Just for notation wise, the inscribed angle we called theta. So now I'm going to describe these 2 halves as, so this angle here, I'm going to call this theta 1, and then that angle I'm going to call theta 2. So what we have is theta 1 plus theta 2, that gives me all of theta, right? That's my entire inscribed angle. And then here, let's call this alpha 1, and then this angle we'll call alpha 2. So alpha 1 plus alpha 2 gives me all of alpha, right? I just wanted to use the same Greek letters here, so I didn't introduce too many new variables, but so we know which pieces make up what. So the 2 thetas together give me the entire inscribed angle, and then the 2 alphas together give me the entire central angle. Okay. Now with that, we can actually use what we know from case 1. So if I look at the top half here, and maybe I can highlight this a little bit so we can see what we're looking at. So we have this inscribed angle here that includes this side plus the diameter. Okay. That inscribed angle is theta, and that central angle is alpha 1. So we know that from case 1, we know that alpha 1 is twice as big as theta 1. And the same thing on the other side of the diameter. So now we have this central angle here, using this side and the diameter. That inscribed angle goes with this central angle here. So that means that alpha 2, that is the same as 2 times theta 2. Okay. Let's take these two equations and let's combine them together. So I'm just going to add the two equations. I'm going to add the left sides, I'm going to add the right sides. So alpha 1 plus alpha 2, that's the same as 2 times theta 1 plus 2 times theta 2. And now I'm just going to do a little bit of substitution. So first, on the right-hand side, these both have a 2 in them, so we can factor that out, like so. Now these two pieces added together, we said that was the same as the entire thing for alpha. So this is the same as alpha. And now in the parentheses, theta 1 plus theta 2, so these two angles added together, that gives me the entire central angle. So that's the same as 2 theta, which again, that's what we wanted to show. So now this entire angle here is half as big as this entire arc. Now we have one more case to go. Now the third case is when the center of the circle is outside of the inscribed angle. So again, let's start with labeling. So we'll call that one theta again, and then our arc, we'll call that alpha. So that's how big these are. And the same thing. We want to show that alpha is twice as big as whatever theta is. Okay. Just like case 2, we want to use case 1 to help us out. So let's start by drawing in this diameter. And then we need a little bit more to work with here. So this was our original angle. So let's draw in this central angle here. So from here to here, and from here to here. Okay, so we're getting some overlap here, but hopefully I can label things so you can see. So this central angle, maybe I'll do another line. So this central angle, this is the one that makes up alpha. So this angle here is alpha. Okay, so hopefully you can see that. So the two endpoints on that arc, connecting those to the center of the circle, that gives me the central angle for alpha. Okay. But now I have the diameter in here as well, so I want to use case 1. So I need to label a couple other things. So this piece is theta, and this little angle here, I'm going to label this one as theta 2. And then this piece, I'm going to label this one as alpha 2. So this angle here. Okay, so now that we have everything labeled, we should be able to use case 1 to help us out. So here we have a central angle, inscribed angle with the side as the diameter. So theta 2, so twice that is equal to this central angle, since they both inscribe this same arc right here. So that's alpha 2. And now if I put the two pieces together, so 2 times both of those thetas, so 2 times both of these, so this entire piece here, and then the central angle that goes with that is all the way from this side to the other side of that diameter, which is alpha plus alpha 2. Okay. So now we can work with this a little bit. I'm going to start by distributing. So 2 times theta plus 2 times theta 2 is equal to our 2 alphas. Alpha 2, we said that was the same as 2 times theta. Okay, that came from our first little angle here. So let's substitute that in. So instead of alpha 2, we'll substitute in 2 times theta 2. And now I can subtract that from both sides, and that will cancel out. And then what we're left with is 2 theta is equal to alpha, which again is what we wanted. Okay, so now we've shown all 3 cases. So we can go back to our original here. So for all 3 of these different possibilities, our inscribed angle is half as big as the intercepted arc.